clima em espuma leve.
Okay, thank you very much. Thank you for the invitation, Dan. How long should this talk be at this point?
Normal 50 minutes.
Okay, well, I'll see if I can move it along. Okay, so the situation that we're interested in is the injection of air into a porous medium that contains a solid fuel. The air will be moving with a certain velocity, and the solid fuel is not going to diffuse. The model was proposed in 2003 and has been studied since by many people in this room. So if I can't answer the question, someone else can. We're going to make a simplification in the model by ignoring the dependence of gas density on temperature. And the motivation is to find a model that's simple enough so that we can analyze it somewhat rigorously, but still reproduces the phenomena that are seen in more complicated models. So what I'll do is, that's not what I'll do. Introduce the equations, discuss combustion waves in the model, discuss the analogs of contact discontinuities in the model, show how these waves fit together to provide solutions of boundary value problems that are analogous to Riemann problems, and then maybe at the end discuss some of the geometry of the combustion waves. Okay. So here's the model. Theta is temperature, rho is the solid fuel, and y is the oxygen concentration in a moving gas. The gas is moving with speed a, and it's transporting both the oxygen and the temperature with that same speed. Gas diffuses, the solid fuel does not, and we're ignoring the diffusion of the oxygen. There's a chemical reaction here which requires both the solid fuel and oxygen, and the unit reaction rate is determined by the temperature. So we're going to call, this should be theta, we're going to call theta equals 0 the temperature at which the ignition starts. That's not absolute 0. 1 is the maximum reaction, unit reaction rate. And we will allow temperatures below 0. That means just temperatures where the reaction does not occur. Of course, we need rho, the solid fuel concentration, and y, the oxygen concentration, always greater than or equal to 0. And the coefficients of 1 here that you see, those all result from non-denominalization. People often do non-denominalization to keep boundary concentrations at 1. We have not done that, and so other coefficients can be set equal to 1.
But the A coefficient, you don't have the same A coefficient by renormalization.
These three coefficients?
No, the first and third equation, you have the same speed A.
Right. When you do non-denominalization, the one coefficient that's left is this velocity of the gas. You can't get rid of that.
You cannot make them equal for the equation.
These coefficients here?
The A.
Oh, the two A's. Oh, I see. Is this on?
This is only
Yeah.
for...
Okay. You cannot make them equal. Absolutely. This is a simplification which makes both these transport velocities equal to A. You're absolutely right. You cannot do that by non-denominalization. That's another simplification we've made, is to keep the two velocities the same. And that is the origin of the title, the light porous foam. This is most appropriate when the porous medium is of that type, the sort of thing you make a mattress out of. Okay. All right. Thank you. Okay, so we're going to be interested in certain boundary value problems. The interval, the x interval, will be infinite. We are going to be interested in fixing all the values of all variables to be constants at the two boundaries. And at the boundaries, we don't want the reaction to occur, which means that either the temperature is 0 or less, that's what we call temperature control. There's no solid fuel, that's fuel control. And there's no oxygen, that's oxygen control. Any of those means that the reaction does not happen. And we're only going to look at the generic case, which means, this is the assumption I call E for ends. At both endpoints, exactly one of these conditions holds, not two at once. You should understand the generic situations before you move on to the non-generic ones. Okay. So what are the combustion waves that occur in this model? What I'm going to mean today by a combustion wave is just a continuous traveling wave. The velocity will have to be positive because what we really have in mind is that fuel is injected at the left end, which means you have a half-open interval and waves with negative speed would not really be supported. So we only consider waves with positive speed. And it will turn out, here's the notation for a traveling wave, a left state to a right state. And these are not necessarily the end states for the boundary value problem. We're going to require that the waves approach the end states exponentially. This is convenient for today's talk. These are the assumptions that give the combustion waves that we'll be interested in. Okay, so the states at which the reaction does not occur, they can be of one of these three types, which this means only temperature control, not the others, or there could be two things happening at once, or all three things could happen to prevent the reaction. We won't allow these at the ends of the boundary on which we want to solve the Riemann problem, but a priori some of these more complicated conditions could occur at interior waves, so we're allowing them for now. This is a notation for the type of the wave giving the two end states. Okay. So here's the result on combustion waves. There are exactly four types of combustion waves supported in this model. Two fast ones, by which we mean that they move faster than the transport speed, and two slow ones, slower than the transport speed. The fast ones are very familiar to us. At the right, there's a low temperature, and both the fuel and the oxygen are there. It's what's called premixed combustion, much studied subject. Behind the wave, either the fuel is run out, so you have a fuel-controlled state, or the oxygen is run out, so you have an oxygen-controlled state. The slow waves are different. They have no oxygen ahead of them, and they move with the speed slower than the transport speed. Behind the wave, either the fuel is run out or the temperature is low. And the story on these slow combustion waves is there's no oxygen ahead, so the gas is bringing the oxygen with speed A. You can't possibly have any combustion ahead of there because there's no gas. So the combustion, if it happens, occurs with a speed slower than the transport speed. In the previous case, any heat that's produced in the reaction is transported with a speed slower than the speed of the reaction. So the high temperature area is behind the wave. With these slow waves, the heat is transported with a speed faster than the chemical reaction, so the high temperature area is actually ahead of the wave. These were unfamiliar to me, but they are in the literature. They go by the names. So names we found for them are reaction trailing smolder waves, or forward filtration combustion waves. So let me discuss the existence and uniqueness of the fast combustion waves. It turns out that you can specify the right state arbitrarily. So this would be a state with low temperature, but both reactants are present. And having specified that right state, there will exist a single fast combustion state with that right single fast combustion wave with that right state. The state behind will either have no oxygen, no fuel, or both. And it depends on, well, the first thing you need is, this is the theta plus is a negative temperature at the right, minus theta plus is a positive temperature. You need a sufficient amount of oxygen or the reaction won't occur. But given the sufficient amount of oxygen, there's a key amount so that if you're below that, it's the oxygen that runs out. If you're above that at the right, it's the fuel that runs out, and there's an in-between state where they both run out at the left. So that's the story on the fast combustion waves. You can count dimensions, and it will even though each right state corresponds to a unique left state, the left states, there's a three-dimensional set of right states, but only a two-dimensional set of left states here, since one of these variables has to be 0. And what that means is that typically a left state will correspond to a one-parameter family of right states. What about the slow combustion waves? They're a little more complicated. For the fuel-controlled ones, where the fuel runs out behind, let me see if I can understand what it says here. Okay. So we are given the, suppose we're given the left state here. So there's no fuel. We're given the amount of oxygen at the left and the temperature at the left, again with that condition that the oxygen is greater than minus the temperature. So given the left state, there will be a one-parameter family of right states that correspond to it. We're allowed to specify the fuel concentration at the right, and then we'll be able to find a traveling wave. So each left state, again, corresponds to a one-parameter family of right states. The temperature-controlled to oxygen-controlled waves are a little different. Given the left temperature, given the left state here, and a right, well, we're given here two components of the left state. We're not given the left fuel concentration, and given the right fuel concentration, the wave is determined. So there's only a three-parameter family of waves, which means that it ought to be that if I switch this to making the the fuel given at the left, if I switch this to having the left state specified, there should be a single traveling wave of this type of that with that left state, not a one-parameter family. And so it's not proven that you can specify the left data, but you can specify three other pieces of data and get the traveling wave. Okay, so what are the things that we call contact discontinuities? So here's the idea. We're going to imagine doing simulations on an infinite x interval. Normally, you will specify some initial conditions which differ from the boundary conditions only on a finite interval. It's the normal way of doing things. And then you will see various waves which propagate with various different speeds, which means that the area in which something is interesting is happening is growing as time goes on. So now you want to follow this for a large time, and you want to see what's happened. So you have to fit it on your computer screen. So you have to shrink by some time-dependent factor to fit the thing on the computer screen. So when you do that, what happens is that there are various funny things in the solution which, once you've compressed the boundary, appear to approach discontinuities, much as the traveling waves, once you compress the interval, appear to approach discontinuities. So this is what we mean by these by contact discontinuities. There are discontinuities in the solution that don't correspond to any continuous traveling wave. On each side, the reaction is not occurring, but there's no continuous traveling wave that corresponds to it. These will propagate with one of the characteristic velocities of the system, which is either 0 for the fuel. If you can have a fuel discontinuity that just stays there, or you can have discontinuities in oxygen and temperature that are propagated with speed a. Now, by discontinuity, I mean once you're looking at a very low interval and shrinking it a lot. Normally they'll appear to be continuous changes. Okay. So once you have this collection of waves to look at, did I skip anything? Right. Once we have this collection of waves to look at, we are going to want to fit all our waves together to get wave sequences. And here's where the boundary value problems come in. We'll specify boundary data at the left, specify boundary data at the right, and see if there are sequences of these waves that can match up the boundary data. And I'm only interested in we're only going to be interested in generic wave sequences. So what that means is we can specify 3 pieces of data at the left and 3 at the right, but we're forced to look where the reaction does not occur. For example, if theta L and rho L are positive, we have to have YL equals 0. So we're looking at a subset of this space where we're allowed to specify our boundary data. And what I mean by a generic wave sequence is that there will be an open set in this space where if I vary the boundary data within that open set, we'll still have a wave sequence of the same type. It's not some special thing. So that's all I say. You normally begin by understanding generic situations before you move on to non-generic ones. Or at least that's a philosophy. Okay. So we're looking at a certain set of boundary conditions that satisfy our assumptions. One further assumption I want to make is that we're only going to allow one wave of velocity 0 and one of velocity a. For example, if there were 2 discontinuities in the fuel, they would both propagate with the same velocity. So after a large time, when you're shrinking things down, that would eventually appear to be a single discontinuity. So that's why we're only allowing a single wave of each speed. There are certain contact discontinuities that can occur in these generic wave sequences and others that can't. A way to figure this out is using what we call a wave number. If a left state only corresponded to a single right state, that's wave dimension number 0. If a left state corresponded to a 1-parameter family of right states, that's what we're calling wave dimension number 1. And if a left state can correspond to a 2-parameter family of right states, that's what we're calling wave dimension number 2. That's why, for example, a discontinuity moving with this speed a, given the left state, I can vary both the temperature. I can't vary the fuel, but I can vary both the temperature and the oxygen concentration at the right and still get a wave of this speed. So I can connect a single state here to a 2-dimensional state here. So in various wave sequences, you want to start here, go to a space of certain dimension, and then add on waves of another dimension, and eventually get to a full dimensional set of allowed right states. And so you can figure out that some of these other contact discontinuities, there simply won't be any way to do that. here's a nice little picture that shows you all the allowed wave sequences. This is the best way we could figure it out to draw it. Waves that start on the left with temperature control and oxygen control turn out to be kind of similar. The pictures look at kind of the same at top and bottom. Waves that start out at the left with fuel control are kind of different. Okay. The speed of the wave is shown by 0A, CS for slow, CF for fast. And the wave dimension number is colored. The red means dimension number 0. You can only go from a left state to a zero-dimensional right state. For example, if you start at a left state that's oxygen-controlled, a zero-dimensional contact discontinuities lets you vary the fuel. The only thing you can do is vary the fuel down to 0. So if you want to get a state of this kind, so it's zero-dimensional. So we've got to get a generic wave sequence, if you're going to end at a fuel-controlled state, so the fuel is 0, the temperature and the oxygen are allowed to vary, there's a two-dimensional set of right states like that, the wave dimension numbers have to add up to at least 2. Or if you want to get to a temperature-controlled right state, since we're allowing a range of low temperatures below 0, there's actually a three-dimensional set of right states near there, and the wave dimension numbers need to add up to 3. So you could trace through this little diagram and find all the sequences that do the right thing and check the little sums of the wave numbers to see if they add up. All right. So let me not go into that in detail. I'm going to give some simulations. So what happens here is that for given left and right states, there will turn out to be typically several different wave sequences that satisfy those that have those left and right states. Now that does not bother me personally because I like to think of Riemann problems as boundary value problems. You're given the values at the boundary, and the solution you approach may well depend on the initial condition that you give. So it doesn't bother me that there might be several, up to 5 in this case, wave sequences with the same boundary conditions. They're just observed for different initial conditions. So for example, if you give an initial condition with very little heat, you won't see any combustion wave. If you give an initial condition with more heat, you might see a combustion wave. Those are 2 different wave sequences with the same boundary data. Okay? So it's not crazy that this should happen. Okay, so here are some simulations. Red is temperature, black is fuel, blue is oxygen. Here we've specified a temperature-controlled state at the left. The temperature is minus something. We've specified an oxygen-controlled state at the right. The oxygen is 0 at the right. And this is that's the boundary data, but this is an initial condition. And so this is what's observed after a fairly large time, and this is not the most convincing thing in the world, but the way we're interpreting this one, what we think would happen if we went longer, right here we see both oxygen and temperature changing. We interpret that as a wave of speed A, a contact discontinuity. There's some kind of there's some little changes in the fuel here that you see, and we believe that those are contact discontinuities, which will now propagate with speed 0, and in the limit, this internal structure is going to get lost, and you'll simply see a wave of speed 0 in which the fuel concentration changes. So some funny business has happened in the middle because of some high temperature. There was a little bit of burning, but it's going to get wiped out in the end, and we won't see any combustion waves. The other simulations are a little more convincing. This is the same kind of boundary. The same boundary data, low temperature at the left, no oxygen at the right, but because of a little different initial condition, what has happened is that we do observe a combustion wave here. Let's see here. Yeah, this is a slow combustion wave that has formed. Over here, the temperature is gradually changing from the temperature of the combustion wave to the boundary temperature according to diffusion by the heat equation. That kind of produces an area of size square root of T, which in our limit would disappear and become a contact discontinuity. That's how we interpret this. And back here is a place where the reaction started, and we see this discontinuity in the fuel, and this will eventually be a contact discontinuity of speed 0. So there are 3 different waves here. So we've seen 2 different wave sequences for the same boundary conditions. Here are some other simulations. This one has 0 fuel at the left and low temperature at the right. And what we observe here is one of our fast combustion waves has occurred here and is moving along. The fuel is complete. The fuel that existed at the right is completely burned up in the combustion, and somewhere this is the oxygen left by the combustion. This is the temperature behind the combustion wave. Somewhere behind here is moving with the speed A. The temperatures approach the boundary condition. So we interpret this as a wave of speed A followed by a fast combustion wave. And then here's the most complicated one I'm going to show, which has both a slow combustion wave and a fast combustion wave. And in here, this is the temperature of the fast combustion wave, the temperature of the slow temperature of the slow combustion wave. And here's an area where they approach each other, which we would interpret as a contact discontinuity of speed A. All right, so there's all these different things that can occur. And actually, once you specify the left state and the right state and the wave sequence you want to use, using those theorems about existence of combustion waves when various data is given, you could figure out exactly what the intermediate states have to be using the theorems exactly the way they were stated. Okay. So what more do I want to say? I'll say a little about how we find the traveling waves in this model, in which the 3-word description is "we were lucky." So here's the equations that we have, and all 3 terms have a reaction term. So you can add and subtract equations, and you can get rid of the reaction term in 2 equations. So here's one way of doing that. I've left the first equation the same. I've done some adding and subtracting so that there's no reaction terms here. This is actually like conservation law. This one also has a diffusion term. We want to look for waves of a certain speed c. So we replace x by this moving coordinate, x minus ct. And the result is that wherever we had a partial with respect to x term, well, it was on the left. I moved it to the right. It's now got an additional c in its coefficient. It's really the only change. And now, so stationary traveling waves are actually stationary solutions of the PDE in these variables. So to find traveling waves, we set all the partials with respect to t equal to 0. These become 0. And now we have some differential equations to solve. And these 2, since they have no reaction term, can be integrated, as you commonly do in conservation laws. Okay. So we've integrated, taken the antiderivative on the last 2. Here, the antiderivative is partial of theta with respect to xi, which I'm naming a new variable, v1. And so when we take antiderivatives of these, we just get constants. These are constants. And this first guy I've written out as a system of 2 two ordinary differential equations. The derivative of theta with respect to c is this new variable v, and the derivative of v with respect to c, you solve for this, and you get this. Okay, so the point is, we're down, we are down to two differential equations and four variables, and we have two constants of the solution. So you can solve for some of the variables in terms of the others and the constants and get down to two differential equations in two variables. And there's various ways of doing that. We've elected to use temperature and fuel as the two variables we keep, and you end up with an ordinary differential equation in those two variables with some constants. And the constants can be figured out once you give one of your boundary conditions will correspond to an equilibrium at which V1 is 0. And so at an equilibrium, both theta dot and rho dot are 0. And given a certain amount of the boundary data, you can figure out what the constants are. Okay, so here's our ODEs with our two parameters, our two parameters, W1 and W2, and of course C, the wave speed that we're looking for, is also a parameter. Different ways of dividing up the equilibria. The fuel-controlled, let's see, you could have rho equal to 0. So the fuel-controlled states are rho equals 0, and then this term here equals 0, and theta and something corresponding to y positive. Actually, sorry, I've got the wrong formula for y here. It's this divided by a constant. So I don't have the right formula here for y, but y is actually determined by the oxygen concentration is actually determined by the fuel concentration and a constant. There should be some constant you're dividing by here. So the fuel concentration states are the guys where rho equals 0, this is 0, and other possibilities are positive. The oxygen control states are similar. Y, which is 0, which means that this thing here is 0, and this is 0, and other variables are positive. There's both fuel-controlled and oxygen-controlled states where both of those things happen. And then I call this TC star. It's like everything else. You have no combustion, and one of the reasons is that this function of theta that determines whether you have combustion is less than or equal to 0. So these are the different types of equilibria. And when we go to look for traveling waves, I mean, you could do this more mathematically, but I'll try to explain it more physically. First of all, I made a change of a notation, which is probably only going to annoy people. U1, U2, U3 is the variables we had before in the same order: temperature, solid, gas. So just, pardon?
I was already proud of you, but I think you kept it until now, so I'm still proud of you.
For keeping one notation this long?
No, theta, rho, and y.
Oh, for so long. Okay, yeah. All right. So now I'll be bad. My collaborators made me do it. Just intuitively, what right states can there be for a fast combustion wave? Well, if there's no fuel at the right, you're not going to have a combustion wave moving to the right, because you can't transport fuel to the right. It doesn't move. When the wave gets there, it's going to encounter no fuel. So you can't have fuel missing at the right. And for a fast combustion wave, you actually can't have oxygen missing at the right, because if it's missing, the oxygen is only transported with that speed A. You're not going to be able to have a combustion wave moving any faster than that, because there won't be any oxygen. So if you want a fast combustion wave, the right state has to be low temperature. Okay, So what I did, we specify the right state, and once the right state is specified, you can determine all those constants and get rid of them, the two constants, and get rid of them, and you just have left the values of the at the right state for parameters. And of course, the wave speed's a parameter in these equations. Okay. In U1, U2 space, which is the variables we left, there will be a line U2 equals 0 that's invariant. If there's no fuel, it stays no fuel. And there's also going to be another line, U2 equals something else that's invariant, which corresponds to there being no oxygen. So one thing that's important is which of these lines is above the other. The lower one you can never get to because there's this invariant line in between. So here's a way of drawing the parameter space. Here's one of our parameters is U3 plus, the amount of oxygen at the right. One is wave speed. Another one is U2 plus, the amount of fuel at the right, which I just marked on the as a point on the U3 plus axis. And then U1 plus, the temperature to the right, turns out not to be important for determining. So anyway, with this, what did I do here? Right. With this notation in this space, there's a curve here that determines which of these two lines lies above and which lies below. Over here, I think the fuel is above, and down here, the oxygen equals 0 is higher. Okay. Oh, yeah, I marked the speed A of transport on here. All right. This line's higher in region 1, yeah. So let's, before we look at either of the regions, I'm going to look at the degenerate case right along here that's intermediate. This means that the two lines coincide, which means that at the right state there's no fuel and no oxygen. So I want to look at this degenerate case first. So we're just going to, here's the sort of diagram we get, phase portrait we get. This is the degenerate right state, a negative eigenvalue and a 0 eigenvalue, which is its sort of unstable manifold, except it's really a center manifold. If I specify U1 plus that's negative, and U2 plus, right, if I specify U1 plus, U2 plus, and C, I will get the phase portrait. There will be a line here on which U1 dot is 0. There will be a bunch of equilibrium back here because with low temperature, it doesn't take much to have an equilibrium. And so here's our right state. We're given U1 plus and U2 plus. Here's our left state. This is this line of degenerate equilibria. Every equilibrium minute has a stable manifold. Here we've got one sort of unstable manifold. It's really a center manifold. We want this guy to connect with this guy to have a traveling wave. And so this is the phase portrait everywhere along this line. As you vary the point on the line, it turns out that this goes from one side to the other side, and because of a Melnikov integral calculation, there's a unique traveling wave of this degenerate type. So that would correspond to a point right there, and the U3 value we call U3 star. And then what happens with higher oxygen values at the right is you get the same sort of picture, except now this is a saddle point, and if I fix the U3 star and vary the C, same as before, I'll find exactly one C where these connect up. So from a certain point U3 star to the right, given the oxygen, there will be a single traveling wave. Okay. It turns out this means this amounts to, given the right, probably said something a little wrong, but given the right state, there will be a single traveling wave associated with it. Okay. Oh, yeah. And, whoops. So I found fast traveling waves to the right of a certain point here. You might think there could be left traveling waves to the left of that point up in there, but there aren't any. Okay, so for the slow traveling waves, it turns out that the right state has to be oxygen controlled. I think we just figured that out from the possible phase portraits. So what that means is that if this is the amount of this is the amount of fuel at the right, wait a minute. Right. No oxygen at the right corresponds to a certain value of U2 at the right, which is the concentration of the fuel at the right. You have an invariant line like that through the right state. And down here, this is the Right, this is the fuel equals 0 line. Right, and in this region, the oxygen equals 0 line, which is corresponds to the right state, lies above the fuel equals 0 line. Right, and so what happens here is that once you've specified the wave speed and once you specified the right state, those two numbers, and the wave speed, a certain line here where U1 dot equals 0 is determined. Once you get into the low temperature region, it's all equilibria, and there's another equilibrium here. So in a certain value in a certain range of C, this line meets the U1 axis, the temperature axis, in a positive point. This is a saddle point. This is an attractor. So you can vary a parameter, and you'll still have a connection from here to here. This is the slow waves that gave rise to a one-parameter family of right states. The other one is more complicated. They're a little different. For a higher value of C, this line goes off to the left. Once I've specified the left state, I've only got one unstable manifold that has to connect to, well, that's not different. I guess what's different? Yeah, right. Before I had a repeller, so it was easy to connect to this saddle. That's what gave the one-parameter family. It's like lax shocks. Over here, the left state only has one unstable direction coming out of it. The right state's still a saddle, so it's harder to have a connection. And this is where we got the corresponding to each left state. There was a single right state, more or less. All right, so I just wanted to do that. So that's all I have to say. The future work is that we are doing. The first thing is to drop this assumption that the transport speeds of heat and oxygen are equal. Fatih Ozbag at NC State is working on that. And the second thing that should be possible is to analyze the stability of the individual combustion waves. There's a whole industry around stability of traveling waves. The ones that arrive in combustion typically don't fit into standard situations, but it still should be possible to analyze the stability of the individual combustion waves to perturbation. That's where I'll stop.